Hola a todos, muy buenas tardes. Espero que hayan tenido un buen almuerzo. Les
Good
damos la
afternoon, everyone. I
bienvenida
hope you
a
have
la
had a good
sesión
lunch. We
Datos y
welcome
Moderación
you to
2035, parte del
Data and
Informe de
Modeling
Descarbonización de la
2035,
30ª Semana de la
part
Energía.
of this
Esta
10th
sesión
week
nos
of
invita a
Energy and
explorar cómo
Power
los
Week.
datos,
This
la modelación
allows us to
avanzada
explore
y las
how
herramientas
data and
digitales
advanced
pueden acelerar
modeling
la
and
transición
digital tools can
energética en América
accelerate
Latina y el Caribe, con
power
miras al
transition
horizonte
in Latin America and in the
2035.
Caribbean. With views
Agradecemos
towards
especialmente a nuestros
2035, we
panelistas,
thank our
moderadores y
panelists,
conferencistas y
moderators,
a todos y todas quienes
conference
nos
speakers,
acompañan
and
por esta
everyone
tarde.
whom joins us this
Invitamos primero
afternoon.
al escenario a nuestra
We first
conferencista
invite
principal,
our
Karen
main
McLaurin,
speaker,
Group
Guy
Manager,
McLaurin, Group
Geospatial Data
Manager of
Science del National
Geospatial
Renewable
Data
Energy
Science,
Laboratory
the
en los
National
Estados
Renewable
Unidos.
Energy Laboratory of the United States. You are recognized.
Buenas tardes, muchas gracias por acompañarnos. Yo sé que es el fin.
Good afternoon. I know it's been the end of a
Y muchas gracias, Olade,
long week. Thank you, Olade, for the invitation, for organizing
Mi nombre es
the
Guillermo
panel.
McLaren,
My name is McLaren, and
del Laboratorio
I
Nacional de Energías
come from the
Renovables de
National
Estados Unidos.
Laboratory of Renewable Energies in the United
Un
States.
momento rápido
And
hablar
a
de
quick
Enel.
moment
Nosotros
to
somos
talk
uno
about
de
of
17 laboratorios nacionales de
us. We
investigación
are 16
del Laboratorio
national
de Energía.
laboratories for research in
Entonces,
power.
nosotros trabajamos en muchos
So we
diferentes
work
espacios de
on
la
many
energía,
different
pero Enel está
spaces in
enfocado
power, but
bastante en la
NREL
integración
is
de energía
focused
en
on
sistemas.
the integration of
Enfocamos en
power
todo
in
de
systems
transporte,
and
generación,
focused
distribución,
on transport, generation,
distribución
distribution,
y los impactos de
transmission,
todos
and
que están
the
integrados en estos
impacts
sistemas.
of everyone on the
Eh,
system.
bueno, esta presentación voy
And
a
this
poner como el
presentation
marco
I
de la
will
conversación,
place
espero.
as framework
Voy a
for
enfocar
the
en uno de los
conversation, I
retos
hope,
que
and I
yo
will
veo
focus
desde
on
mi
one of the
perspectiva como
challenges I've
experiencia
seen from
modelando
my
sistemas
perspective, my
energéticos.
experience seeing
Eh,
power systems.
Voy a hablar de
I
tres
will talk
preguntas
of
que
three
tengo, que voy a
main
responder.
questions that I have
Primero,
and will answer.
un
First,
ejemplo,
to give an
puede ser que la
example
pregunta cómo vamos a operar
of
el
how
sistema
we will
eléctrico del
operate
futuro.
the
Y
future
también
power
un poco de
system.
contexto de
And
cuáles son
also a bit of
los retos que
context
nos
that when
vamos
we
a
say
estar.
the future, what we
Y
should
bueno, la mayoría
anticipate.
voy a hablar
And well,
de
the
los retos que yo
majority,
veo
I will talk of
usando un
challenges that
ejemplo
I
de un
see
estudio que hicimos.
using an example that we did
Los grandes retos
of the
en
greatest
datos y
challenges
modelos
in
de sistemas
data
eléctricos.
and modeling
Y para
power
terminar, cómo
systems.
vamos a
And to
avanzar
finish of
en la
how we will
modelación de modelos
advance this
para
community
superar estos
mod
retos.
in modeling to
Bueno, para
overcome these
empezar,
challenges. Well, to first
quiero
start off,
compartir, esto es
I wish to
un estudio que
share
hicimos
a
hace
study that
unos
we've
años.
done
Se
some
llama
years ago
North American Renewable
called the
Integration
North
Study.
American
Era
Renewable Integration
de
Study,
Canadá, Estados
which
Unidos y
was
México.
from
Y
Canada,
esto fue
US, and the
una
United
colaboración
States
con los
in
gobiernos de los tres
collaboration
países
with the
y los
governments of the
centros de
three countries
investigación de los
and the
tres
research
países.
centers of the
Como
three
pueden imaginar,
countries.
eso fue un
As you can
trabajo muy
imagine,
grande.
this was
Los
large work
diferentes
done with three
países
different
y todos sus
countries and all
unidades
of
de datos
their
de modelación.
data entities
Esto es
in the simulation.
un modelo de un
This is
sistema
a
eléctrico del
model
futuro. En
of a
particular, ese
futuristic
es un
power
escenario de
system. In
descarbonización
particular,
del
this is a
80%
scenario of 80%
del
decarbonization
año 2050.
of
Entonces, primero
2050.
déjeme explicar lo que estamos
So
viendo.
let me first
Esto es un
explain what you
día
are looking at. This is
de carga máxima de
a
verano de
maximum
fin de
load
junio.
day at the end of
Se está
June.
viendo
You are looking at
el tiempo pasar ahí. Tenemos esa línea que
time pass.
representa
We have that line
día y noche.
that represents day and night.
Eso es una agresión. Voy a hablar un
This
poquito más de lo que está atrás
is
de ese modelo.
an
Pero estamos
aggregation. I
viendo
will talk a
el
bit
flujo
more what's behind what you're
de
looking at.
electricidad, la
Power
transmisión
flow,
entre
transmission flow
diferentes
between
operadores regionales.
different
Estamos
regional
viendo, ese es el
operators.
modelo del
You're
despacho.
seeing this
A 5
model of
minutos, ve
dispatch
arriba el
at 5 minutes.
reloj. Estamos usando
Look at
datos
we're
solarísticos
using
de 5
data,
minutos para
five
representar esa alta
minutes data
definición
to represent
de ese movimiento, ese
this in
flujo
high definition of
de
the
electricidad en el sistema.
flows
Entonces,
of electricity
la
in the
generación,
system.
esas
So
bolitas
you
que
can
van
see the generation
subiendo y
here, the
descendiendo.
balls that expand
Arriba a
here.
la derecha ve
Upper right, we
la
can
clave
see
de los diferentes colores. Tenemos
in the key, the different
básicamente
colors.
fotovoltaico en
The
amarillo.
photovoltaic in yellow,
Tenemos
we
azul
have
oscuro eólico
in light blue eolic,
y en azul claro
and in
arriba
blue and light
es en
blue,
Canadá,
Plus, further to Canada, we have the hydropower. And another point that I wish you to look at is the right bars. We have a line there, and this is the charge or load of that system operator. So we will have to see that there's sometimes more or less than the load produced. The lines between them on the map is the electricity that's being imported and exported. Thus, it's important to know and mention here that we have and share power interconnection with Canada and with parts of Mexico. But we are modeling it towards a future system where we have more capacity to transfer electricity between the different interconnections of the United States, like also with Mexico. We also have here the variable generation curtailment, and I don't know if you can see it from the back clearly, but every system, every operator in the parentheses show a percentage of variable generation curtailing. So I wish to use this example for the study because we find millions of challenges along the way, but this is to formulate one of the main challenges of the space. I wish to first say that I will end up more or less talking of electrical system models, but among them there are many different types of models, many types of replications and questions where we're using models to understand them. This model, behind it, has space and time measurements of resolution, and at the end of June, 5 minutes of temporal kilometer. We have representation of axis of the Earth, and we use a 90-meter mesh to model where we can build and cannot, and also the supply of generation. And then we use a capacity expansion model called reads from annual, and it simulates the evolution of the power system according to different assumptions, different political assumptions of innovation and cost and ways of restricting the model, which advances from current till 2050. So, for example, you can place and restrict that the model reaches a point of 80% of decarbonized system. And then what you see is a Plexus model. I will mention this, but I see many have heard of the Plexus model, which is used frequently. This is the short-term model that's most frequently used. We are using it to model electricity production cost and mitigating transmission congestion and access. So the first challenge that we find was that data, space temporal data that cover the whole continent, and the variable resources are eolic mainly, or wind power. And I wish to make use of the moment to share with you, to the right, these are data that we've produced for many years in all of the continents of America from a national solar database. And what we wish to share with you to the left is that we are finishing a new database that will cover all of South America of high resolution, 2 kilometers in space and 5 minutes in time, that will cover 20 years from 2005 until 2024. This data is all produced from space, are free and public, and we try for them to be of easy access, easy use, and easy integration to other models. So a sneak preview to contact me if you want to contact me. We will publish the first 3 years this month and the 20 years at the end of 2025. Well, this obviously I mustn't mention why the model is important. It represents the variability of these resources with high resolution. This is the important point here, where we can't use MERA2, or this is the analysis that has a large pixel to it. So it gives us the information and doesn't represent variability of the resources that we need. So this was a very large challenge. We had to produce all this data for the study. And I also wish to mention that prognosis and prediction is what we need. There are different entities and research centers and models to produce these predictions, the 6-hour prediction and forecast of head. But likewise, this is a challenge because some have a cost. And of course, the idea is reaching a point where we mustn't pay for data, which are fundamental for our models. Well, talking of resources, South America and other parts of the world is very important. So a challenge that we found that I see in Latin America is to have representation of public data for the whole content to model, which represents precipitation and variability of what I mentioned for the companies, and also the correlationship with the resources that we have in all of the countries of generation and hydroelectric power production. So they are all connected, and it's important for these models. And I wish to mention geothermals because a lot is coming and lots of innovation is coming and great opportunity is seen. Specifically, we are researching newer technologies of open circuit and closed circuit, EGS, CI, and AGS, which do not need geothermal fluids, just the water. With hydraulic fracturing, you can create the connectivity needed. So the analysis that we have done tells us greatly of where we can deploy the technology, because we are now restricting how we can restrict heat, connectivity, and fluids for hydrothermal generation. So an important resources to model and has a large uncertainty to have. We've had a panel this week with geothermal resources where there's quite a lot of certainty here. So it's important that we understand this certainty and work with industries so that they can obtain better information to analyze the exploration risk and to begin to drill wells for exploitation and exploration. So, another figure is the data that represents technology. We not necessarily need the same space-time resolution as always, but we don't have databases that cover the whole continent in the way and in the resolution we need. And to finish with resource, how will climate change and how will the extreme meteorological phenomena impact? So what you see here is a true phenomenon where we have at the moment a huge community. There are excellent models that are forming the range of the impact of the climate change and helping to understand certainty with the different scenarios. This scenario 4.2, SCP-2 4.5, the problem with the model is that these are 100-kilometer pixels, and there's an estimation from a state of 2020 variables that, for example, up top have temperature, in the middle wind, and at the bottom solar radiation. So an estimate per day does not help us in electrical systems models. So what we need is a model that increases space and time resolution. So as I've mentioned, these are models where we've placed it all open code. We were talking with colleagues in Chile to see the opportunities where they can take the model and produce data for Chile. So We work greatly on producing tools and models, and then to try to build a community. And that's what I will talk about, the community of all scientists whom talk about models. But it's important that we have representation. It will change. For the solar resource will change, the wind power resource will change with seasonal patterns that will impact. So we need to understand and to have a representation of these changes. And this graph, nothing new is seen, where we have power outages in the United States, as seen all over the world, which are caused by meteorological causes. And we can see more of these events every year, which are more and more extreme, with higher and higher impact. And we become more and more vulnerable. So it is important to truly represent these heat collisions, cold waves, hurricanes, everything that has an impact upon electrical systems. Well, the next challenges for data is representation of power load. So, Amanda changes, and we have more load in the cities. We have different load levels of the type of industry that exists. So, in these examples, in space and sectorial examples, we have the representation of the load at a provincial level or at a state level. Maybe enough for some models, but for many, it is not. So there's a lot of methodologies of deaggregating, as seen here to the right, of the real data that have been reported, which we can deaggregate here. We could see at the level of the lock, and also temporary representation or time representation of when that electricity is being used. And much of the data represents, since it has a profile per sector per region. So it's the spatial segregation, space and time separation, and also through sectors. So we've talked this week of the data centers, which will be new loads, huge new loads, which can be built quite quickly, and we have quite a bit of need for these centers. And they will change not only where we have the load or how much load we have, but there are complexities. There are temporary complexities related. Some can be managed in different ways, the temporary profile, and others have less flexibility depending on the sector and the use of the data centers. Transmission. I worked on studies around the world where representation of the transmission systems is the most limiting factors for us. I understand this. Governments have concerns or very sensitive concern for safety of publishing their data from the transmission networks and to have all of the detail available on internet. Here to the right, we have a database that you can find at energydata.info, which has its use. But this data in many countries mix transmission and distribution and does not represent the voltage of the lines, which is important. But I wish to say that starting with this, we don't need a representation each line or each substation. So here in the middle is the representation we use at NERES. So there are many ways of adding the transmission hubs and the lines to represent how we can support these changes and the expanse of the power system and at the system for transmission and at the same time for transmission. And there are other analyses that do require detail. This is a model that my team manages that estimates when there is a site that will have a power plant built, generation plant where the closest substation can be found and what would be the most best route and least cost route. And when we have a wind power plant where we call it the most direct when considering topography and access to land and other concepts, it connects. And then in the reality we wish to represent will have costs to improve maybe and improve line capacity or substation capacity. So the point is that specifically, this is a very complicated area of many challenges, and we can be very practical. What we need to represent, to adequately represent.
Bueno, una de las partes más importantes es la digitalización y el acceso abierto. Entonces, un ejemplo que Ivo me compartió, que OLADE está desarrollando un dashboard de la generación en América Latina, que es un esfuerzo que admiro mucho. Eso nos va a mover muy adelante, porque para todos que han hecho ese tipo de trabajo, gastamos meses y meses solamente descargando los datos, formateando los datos, encontrando lo que nos falta y cómo lo vamos a conseguir. Entonces eso es mucho tiempo.
Making sure that we are going to get this, and we are trying to represent this information the right way or throughout the continent when we're using this kind of models. So we hope that there are a lot more efforts like this in all the data that I have mentioned. We cannot continue to keep our data in PDF. We need to have a format where everyone can interact with that data. That's why APIs are so important. They're such a nice solution because they can be modified easily using Python or R or the language you want. We need to focus on that of the APIs and open source code. To change the challenges I see in the models, first is the flexibility and interoperability of the models. We know in Latin America is a perfect example because every system has different challenges and different limitations, different resources and opportunities, also energetic markets. So this is a figure from a publication last year that I think is interesting. Just to show you, because we have a lot of energy models in the electric system, and they are used in different applications. To the right, you see models of transport, generation models. There are several of them. They're all different. They'll have their pros and cons, but we need to get to a point where we can take advantage of all the models in a more flexible way with more interoperability. We are using 5 big models for these studies, and it took us so long to work in the interoperability of our models. So that's an important challenge. One that's not here is Plexus, is the methodology of this paper, but I thought it was interesting to show how the variability of tools we have. Well, something important to consider is fidelity, resolution, and the broadness of the models. How much does a model fit? Because we want to represent everything that's important, but it's almost impossible to represent everything in one model. So we focus on what's necessary for the questions we're asking with that specific model. So we have many different resolutions that can be the dispatch does every hour, 5 minutes, 15 minutes, how many regions can use the model. And many of these limitations are related to computer limitations. Our model of capacity expansion has a lot of limitations. We cannot dispatch 5 minutes minutes because we have a big server and it's not enough. We can run Plexus every 5 minutes, but our expansion model, we can't. So we need to find that balance, but thinking in the geographic coverage, the representation of the resources, etc. A lot of considerations on what can the model fit. And that's a challenge, and we're always looking at the pros and cons. Well, to wrap it up, the challenges that I see in the foundation of all of this are transparency, validation of data and models, and trust in the model. So the community of open source is growing very fast, and that's something that will help us in this space, because if the model is a black box, it doesn't help us to foster the trust of those making the decisions. So open source helps make the community grow, and the community improves the model, and it's focused in the reproducible analysis. So for every study, we need to replicate the exact same way we say it. We have to use data and model of open source so others can reproduce this analysis. And again, in relation to this, there's accessibility and costs. Plexus is a great model, we still use it, but there's a cost assigned to it. So maybe it's not for a great operator, but it's enough for, it's big for a university or for a small consultant. So that's another component. But to go back to transparency, there's an initiative that I like very much from Stanford University that's called we don't have something like that in the energy models. I just wanted to set it as an example, but they have an index of how transparent models are. And that's for artificial intelligence models that are being used by Google and Meta, and that exposes models that still are black boxes that are closed and don't let people look at the code. And that's what I like, to put it out there. And lastly, validation is very important. It's hard to validate an electric system model, but that's something that we need to continue to do. Not in a validation point of view, but verification. We need to verify all kinds of models. So right now we need to do that for you to gain more trust in our models. Well, to wrap it up, actually, I placed I wrote some challenges, maybe some solutions, but leaving this open as a work for the panel to discuss some of them, and some others that I didn't mention that I can imagine that the panel will be drawn to. But we need to look at a way to close the gaps that we have between the public sector, private sector, researchers and operators, because we're not speaking the same language in the context of data and models. Even if many of the data that I mentioned, many are closed, private, so, and for reasons that make a lot of sense. So it's not easy. It's quite difficult to close that gap, to bridge the gap between operators and researchers. Something that is being talked about is the technical capacity. And that's simpler when you have a bigger community, because they grow faster, easier with open source data and open code. And the idea there is to foster communication, the technical communication. We're talking about esoteric, complex things, and the way in which we communicate it to those responsible of making decisions. This is important. So data and models have to represent everyone in the countries we are modeling. And they need to improve accessibility, flexibility, and trust for everyone. So again, thank you very much, and thank you for being here.
A continuación,
Thank you, Galen. Now we will give the floor to Andrés de Tomás, a senior specialist from the World Bank, who will share a small presentation with us. Thank you, Olade, for inviting us to be a part of this panel. Let me see if I find the presentation. The idea today is to share with you experiences in the world of the World Bank. My name is Andrés de Tomase. I'm a part of the World Community of Energy of the World Bank. And I will share with you today 3 subjects related to those presented by the previous speaker. We're going to be talking about the expansion of generation, the real case of planification of distribution with the support of geographical tools. The perfection's enemy of good. We're going to be talking of the Horn of Africa, of which Somalia, Ethiopia, and Kenya are a part of, and how the geographic tools, without the need of the specific place, the team of the bank was able to conduct a preliminary planification and green planning, and we will talk about the experience of the bank in the use of geographic experiences to assess risks in projects the bank assesses. Now, when we talk about expansion and generation, any tool we have, when we want to project, we're focusing on 2 goals. These tools, in the first place, have to look to minimize the cost of energy in the future and determine what technologies to install, what power to install, and when to install generation. So when we install these models that are too advanced, they provide this kind of information. The criteria, far from the excellent tools there might be, have to be very clear, which is the supply demand with security and certainty. This is something we need to work on in Latin America. How much is it to fail? Is it good to see a planner like the ones in Brazil who apply fail costs for $3,500 per megawatt per hour, because that will ensure that the sector is investing to supply a good quality service. Energy independence. Everybody is talking about interconnection, but if you worked on it, you know the goal from a country from the point of view of planning is to ensure the service in an internal manner from the electric point of view. We're an island. That doesn't mean that then we're going to get opportunity costs with nervous and neighbors and explore the advantage of being interconnected, but the policy will always be independence from the point of view of the installed power. Resilience, we have to have a resilient system, not only from the climate change point of view, what happened in Europe with the dependency of gas. Here in Latin America, always had good practices, and this is not a good practice from Europe, who established everything just based on Russia's gas. Country policies, this is another criteria. We need to work on the expansion plan and defining country policies. Environmental, for example, I'm just going to have to pay for it. Of course, we all want to eliminate everything that's not green, but sometimes it's not possible, it's not feasible. And lastly, we can add to this criteria, for example, what happens in Tajikistan and Mozambique that have hydric accidents, and they need to think, what are we going to do with this? Maybe I have neighbors who need the energy, and that's a part of the expansion plan. So what happens when we don't plan or implement well what we plan? Because what you will see in the sector, especially in Latin America, is that we have great planning, but the execution is quite poor. And we
para desarrollar una línea de transporte, por ejemplo, un proyecto de generación. Y en ese cuadrito muy pequeñito tenemos un ejemplo de qué pasa cuando planificamos y no implementamos. Es el caso de Ciudad de Cabo, City of Cape Town. En el año fiscal un cliente promedio de Ciudad de Cabo experimentó 79 horas sin servicio. Este es el average system interruption duration.
Cabo experimented several cities without service.
Son más o menos similares. De esas 79 horas sin servicio, 76 estuvieron relacionadas con problemas.
79 hours without service, 76 were related with problems of lack of generation. That's what happens when you don't plan what you have in time and from. So we need this to ensure a minimum cost future. We need a calculator, a platform, a support. Of course, we have Plexus, we have ideas from Lepres, Genex, MIT, Auroras, Genex. We have so many technologies that can support us. Here I'm showing you a picture of a free software. I could have shown you anything. What we need is a calculator, where we need to have two inputs, one related to the system, generation, demand, electric network, interconnections, and another one that's from random sources. And here's a problem, this randomized sources that we'll talk about hydraulicity, the wind, the prices of fuel. Who knows with certainty what the price of fuel oil 06 will be in 2 years? The probability of being right is very low, and this tool that could be any of these that we mentioned above has two axes. What defines a policy of operation and expected costs. Here in Santiago, the bank has worked with the University of Chile. They have a great tool that we are using in the bank in the Dominican Republic to do the same thing. We get different stakeholders and horizons when we talk about planning. We have short term, which is the reservoirs, automatic, the auxiliary services, that's done automatically, a system of automatic control. Then we have midterm, which is the demand in charge of the national dispatch plans. And then we have, this is not an opinion from the bank, we have Brazil as well. They are number one in planification reference, and of course we have many others who have not advanced a lot in the subjects, and we think that just having this tool like Plexus will solve all the issues, and that's not correct. Well, what do we use this for? Here I will show you information from the International Energy Agency and British Petroleum. What are we expecting in the future if we pay attention? For 2025 at a global level, we are forecasting a closing of 3,600 terabytes an hour for global consumption. Meanwhile, for 2025 is 40,700. So what's the participation of wind power and solar power? If we talk about installed power, we're going to be at a 44%. This is supported by the capex of solar, which has gone down a lot. And because the planners within their models, they have learned to value the installation of resources that have a zero variable cost. That provides resilience and makes us immune to the variations of the price of fuel. So this is the forecast of the International University Agency, and we have the British Petroleum that has this long-term forecast to 2050, and they are looking at the same thing, that for 2035 the scenario will be similar to what the International Energy Agency is handling right now. But they also wonder what happens if we are more pro in the reduction of carbon emissions, and we need to be clear about that.
Now we've talked of basic tools for preparing plans for generation. Let's talk of the real world, a real example, which is the case of the African Horn, Ethiopia, the Loop Sea, Somalia, Kenya. As I've mentioned, in 2021, a team of the bank which I led had to plan a preliminary expansion of this distribution system where frontier areas between all of these countries, where we have very little information of statistics and inventory, and also there are conflicts. We have the IDPs, the internal displaced people, IDPs, people whom are displaced internally. So here we had 70 sites and we make a space. We didn't expand these isolated areas. How do you propose that an expansion system? And what we did, we said we had top overviews, where we can use tools, Google Maps and other sources. And we work with a very strong team of experts in geographical bank systems. And what did we do? Well, we were capable of delimiting the perimeters of the roofs. The roofs that we observed in these top overviews, we could calculate the surface area, something that couldn't be done, but now can we do is to calculate the height of the roof. With an aerial view, we can see a home. Now we have current capacities to calculate the height through other tools. And once the perimeters of each of the rooftops are defined, we had the capacity of contrasting with other layers. How far is that rooftop from a path and road bar? Is it from the existing network? So, and we were able to count the amount of roofs. We use a geo area algorithm from the points of supply, the points where we would localize the facility and easy areas for generation, and in each geo area we were counting the amount of rooftops. Well, what we see here is part of a project. We're looking at the frontier areas. The 4 countries analyzed. This area is defined basically by a strip of land of 40 kilometers buffer, and here we placed different layers. And on the right-hand graph, you can observe that we were able to count, without going into the field, 1,295,000 rooftops, of which practically 480,000 were close to mid-service existing, 11,000 volts, 15,000 volts, 30,000, 33,000 volts, and of which 361,000 weren't as further than 10 kilometers of point of supply. And on the other hand, we had true, real information of the Kenya Power and Lighting Company, the KPSC, and we were able to function according to the sizes of roofs, the consumption. This is mid values. This is just Gaussian distribution. You could play with standard deviations to know how far it is from reality. Well, here we're looking, you're seeing part of the work done. We're seeing here the layer of localizing networks, the localizing layer of generation points, and other layer types. And finally, the result, this is something which in Latin America is needed. I understand that you can make the most of a case like this in rural areas of Guatemala and Honduras, Nicaragua, and Bolivia, where there's very little statistical information, and where to find what's perfect would be counterproductive. So what was obtained? Currently, this system made up of the 40-kilometer strip of land, made up of the 4 countries. Well, at that moment, we gave service to 137,000 supplies. We could give a distribution proposal of expanding of 15,000 to go to 30% of electrification to 70% of electrification among what is 10 kilometers, defined a radius of 10 kilometers from the point of supply. This is important because if the need to go into the field, without the need of going to the field, we could do a preliminary design where we would have to go first and to materialize this and to look the natural necessary resources. And obviously this means that then each of the countries had to do their own detailed engineering. Well, this is basically a true example, and now just to close, because time is running, I want to show a tool, a quite new tool that we're using in the bank with our expansion projects. We work with many power companies which operate under global bank financing. And what would happen to us, or what happens or still happening to us, is that there are many projects still of engineering projects that lack necessary information. This is the case that I will share with you is the Dominican Republic. One of the 3 hydro plants presents a project to the Global Bank, a detailed engineering. What the bank does, the GFDR Bank, the Global Facility for Disaster Recovery, that the bank prepares a study that I will show as interesting, which some way assesses how resilient or how exposed to risk is that proposal for expansion. And here we have to the right what was given in the detailed engineering by the power company, one of the Dominican Republic power companies. They will develop 750,000 kilometers of network in around $50,000 per kilometer. So a lot of money invested, and this was their proposal. We have detailed engineering, and we will make this assessment, this risk assessment, that in some way considers danger, concept positioning, vulnerability, risk impact, and climate concepts. And here we have the tool that the bank developed. Basically, we work with different geographic layers. Here we have a bottom layer. Here we have, see how we propose using the proposed layer. We said, as a colleague mentioned, what happens now? How exposed are we in flooding by 2020, but also by 2050, which is quite different in the situation depending the area of the globe. Specifically on coastal areas, you will see that differences change and greatly. This is an island in the Dominican Republic, and we're looking at in blue in intense high risk areas. This detailed engineering that this company is presenting is not prepared and does not consider in their definition of this high flooding probability areas. To the right, you will see another risk, which is landslide risk. And clearly see that there are areas in dark ground where we consider an extremely exposed to risk area. These are maps from NASA which are available. What other risk? How about forest fire risk? These are things that in Chile, I think, are assured, but these are things that in the Dominican Republic are things that you can see that maybe are not considered usually. Regarding forest fires, the risk is quite low for the project. The layer of the land cover practically, and regarding temperature and the capability of transport and design presented by these companies go quite in hand with environmental temperature. You can see there's not as high risk due to temperature in this case. And finally, we have other two risks. The Dominican Republic is exposed to cyclones. We see this map here, which the probability of facing winds, 50 years of returns, and the probability of facing winds of 50 to 60 meters per second is around 200 kilometers per hour, right? Is quite high in some areas of the island, and this has to be considered. And regarding danger and earthquake risk, clearly we have elevated risk, elevated seismic risk. And finally, and I can close with this, time is short, we have other two geographic layers that we apply on this engineering proposal. One that is localizing critical installation. If you use OpenStreetMaps, for example, you can see where hospitals are located and emergency installations, civic centers. It's clear in this case you can see that control this company does not mention these critical centers, thus do not require additional efforts. And finally, a very interesting layer is the decrease of night illumination with NOAA maps, which in some way you can see how much commercial activity do we have in these areas. And to finish the presentation is what we wish to share were real cases that with basic information, one can somewhat ensure the proposal for the design does not have barriers related to risk. And well then, I will stop then, and thank you very much, everyone. Thank you, Andres, for your presentation. We will call you soon to come back to the panel. But first of all, we wish to give space to Ivo Nacucho, who will moderate the panel. Ivo is Olares' consultant. We will now go once again to Andres. And Andres, if you can join us on the stage, together with Bernard Joss, General Manager of the Germany Operation, Landin Barrot, Officer of the International Agency for Power, ELARI, Managing Director for Energy Transition in Accenture, and Maximiliano Percent, CEO and Founder of Energy Transition. Please, if you may. Good afternoon. I appreciate that since it's being Friday at this time after so many years that you still stick around. It's an honor. To be honest, thank you, Jose. Thank you, Galen, for the very educational and didactic, and we will probably mention several things. I would like to start with landing, because one of the subjects that Galen mentioned in his presentation is the difficulties of trying to work with quality data that is open for all. And in this sense, we all know the excellent work of the International Agency every year, but that's the glamorous part, right, of the work that they do. And I always am interested in being someone who likes data personally, that to tell us, Blandin, what challenges does it represent to have a periodic report of such level of detail? If there are lessons that you can mention to us regarding what would be the pain points and failure and good parts maybe, and if it's interesting for you to mention the instance of the biannual technique that you do and the framework. Thank you very much, Ivo. And thank you for the invitation. I would like to ask, apologies, I'm going to speak in English. And second, I have several comments. And please stick with me. And once again, thank you very much.
English with apologies again. So since the 1990s, the IEA produces its yearly World Energy Outlook, las perspectivas energéticas globales, which contains forward-looking views into the global and regional energy and carbon emission trends. So again, it's a yearly exercise. This is based on a large-scale simulation model, which we call the Global Energy and Climate Model, GEC. This model we've been running since 2021, when we coupled our global energy demand and supply model, which is an optimization model, together with our technology perspective model, which is much more of a bottom-up. And we are currently drawing projections until 2050. We're using historical data ranging back from 1970. Just to give you a bit of context, I believe many of you are familiar with the scenarios of the World Energy Outlook. Now to your question, I would maybe like to share 4 points and 4 recurring challenges in getting this annual global and detailed projections out. The first one is has to do with the fact that the world exercise on the availability of country-level data, which needs to be robust, accurate, and up-to-date, as any good statistician will tell you. The IEA gets national energy balances from the countries themselves, typically on an annual basis. These balances and the statistics we produce on energy prices are the cornerstone, really, of the World Energy Outlook, the WEO, and all the special reports we produce. So when you find a regional report there was one in Latin America in 2023, or a report focusing on a sector, we also are designing net zero roadmap for countries. This is all based, originally on country data provided by governments themselves. But of course, not all national energy accounts are the same. Governments and countries are in very different situations. There are very unique underlying context, each of them. And so the agency has developed a dedicated roadmap to help countries design and strengthen their national energy statistical systems. I won't be too long on that because obviously there are other speakers, but I really invite you to have a look into this roadmap for national statistical planning, funding needs, setting up the financial, human, and technical resources. The legal aspect of data collection management is obviously central. And the third pillar is tracking the data, implementing some data collection methodologies, and obviously quality checks. So that's for the country level aspect, the country data, the country input. Obviously, we do use other sources when data are not there or are just not enough. And I think it just requests countries to fill out these BTRs as part of the transparency framework that was funded with the agreement. And it's a goldmine of excellent data. And it actually, helps you when read in conjunction with country indices to really understand what countries are doing and where they're trying to get. So again, today there are around 100 of these BTRs available, and I really encourage you to have a look into that. Maybe getting a bit faster into the 2 other challenges. The second challenge is about anticipating and understanding the changes in the global energy landscape. When you do this type of yearly exercise, getting the energy balances, again, as I said, is just a start. With modeling, a lot, if not everything, depends upon assumptions, as you know. And for these assumptions to be valid, you need to understand the drivers for major changes. And these sometimes are hard to fathom. Our modelers are, it's a big part of their work, to understand how the world is moving around. You constantly need to be on the hunt for these small signals that will be announcing megatrends. These look like, I'll just give a few issues that really looks like obvious and very central now, but the IEA has actually been investing decades of work to understand them and advance, investigate the underlying trends. So everything related from on the implication of the rising demand for critical minerals on the energy sector and on the constraints it places on clean energy transition. Another topic has to do with the implication of the rise of AI, artificial intelligence on energy demand. Again, it's all the rage now. Everybody's talking about it, but you had to, from very early on, try and, detect what the potential impact could be. The impact of extreme meteorological events on power system, as you just mentioned, is also a growing concern. And again, you need to invest, you need to investigate, you need to invest literally in your modeling a little bit in advance in order to, when the time is ready and when you have enough data, input it into the model. And obviously cooperation with other data providers and the private sector is very important to get, these trends right. Again, quickly, third challenge is scaling down the analysis. Same as for IPCC models, it's always, I was about to say, it's always easy to get global trends. It's not. My colleagues are going to kill me. But no, it's easier to get global trends than to scale down what is happening at the regional or country level. Again, our model sees the world as a connected system of 29 regions. We all know it's not like that. And so we have been working very hard over the last year to zoom in, and we now have like 15 countries in the model, including, like modeled by themselves, including Argentina, Brazil, Colombia, Costa Rica, Chile, Mexico, but much more needs to be done. And the very last point I wanted to share, embracing the complexity of the real world, which is something that is always every year a massive challenge. Because aside from technical competencies, the best talent a modeler can have is probably humbleness. We need to be humble with the results of our modeling. Projections are not predictions, and they should be presented and handled as such. One of the ways to remain humble is to constantly work to be as close to real world action as possible. I've just talked about hard data, quantitative indicators, but qualitative data is also of utmost importance to projections. And I'm thinking in particular about government policies and even company policies and targets. Understanding and feeding the modeling with those is very important. It's tough, but it's a necessary job, to gauge what exactly is being implemented, what impact it will have on, a given sector. And on this last point, and before, passing the floor to others, I would just like to point you to the policy tracker that the IEA maintains. It's something we've put online over the last year, and it covers a majority of countries across the world. So if you want to understand what governments are doing on energy policies, this is the place to be. And yeah, I believe that was long enough. Thank you.
Do you hear me? Yes. Okay. Thank you. Okay, continuing in English, I will ask, and sorry because we are trying to compress the time to the rest of the panel. So maybe the two questions originally was thought for the panel. Maybe I will try to synthesize in one. But going to OET, I don't know if any of you knows about open energy transition. Open energy transitions. Here's CEO here, Max. They do a really good work in making open source tools for modeling and for data collection. So with that in mind, I would like if you, Max, can briefly explain what open energy transition does, both in the planning space and also in the data collecting space regarding maybe the Map My Grid initiative.
Right. Buenos tardes. That's my Spanish. Thank you, Ivo, for inviting me. I can hear me twice now, which is a little bit irritating. Yeah, OET, like probably a lot of people don't know us, but we're actually the second biggest open source contributor in the world on the open source planning space. Number one, I think, is currently NREL. So like we have the STAR institution here. There are a couple of others as well involved in open source, like grid operators, regulators, and many others. For people who don't know that, open source is actually a global trend. Like we actually did the math last week. We have an open modeling tracker where you can see how popular different tools are. And we count now 2.5 million downloads, known downloads of open source energy planning tools every year. I mean, like that's crazy. A lot of people don't know that. So, and what OET does is really like we're working from the data input side, like the downstream stuff, up like then also on the model enhancements, like we're doing software development, software enhancement to open source tools, and on the data side, but also on the open modeling side, and working then also in like improving insights for energy planning studies, resilience studies, and so on. Like we have really the full supply chain of this open source model that we tackle. Yeah, our focus is really like making those tools commercially ready. We heard many times Plexos and other tools. I would just underline Plexos is the current market leader, really, with, I don't know, huge market share. And yeah, like we are really like identifying gaps between open source, the open source ecosystem and the proprietary one, and closing the gap step by step. On the data side, like we heard, like there's maybe one initiative that I want to mention, and like that's the Map Your Grid initiative. We heard from NREL, but also from the World Bank, that grid data is very important. Yeah, but the fact is that we just know roughly about 70% of the grid where it's located. Like 30% is unknown. We have no clue where it is. And like we currently have this Map Your Grid initiative ongoing, where we contribute within the next 3 years, and like that's our target, to complete the whole grid coverage globally. And that's already partially, like we already get partially funds, but you know, like if you're interested actually in supporting this work, like we just need 3 million euros for 3 years, you know, like 3 times 3. That's great. Yeah, but with that, you know, like we know where the grids are. Very important for disaster management, for studies, independent planning studies, and so on. Yeah, and here it's really key to also support creation of the like source data. People just modify existing data. And others. Okay, the mic is not working anymore. But yeah, it's kind of key. Anyways, I'll just leave it here, and I hope I answered what we're doing, and I hope now when you leave the room, like you know who's OET.
I don't know, I'm having... Ok, perfecto. Bueno, ahora, ya que estamos entrando y saliendo de idiomas y entrando y saliendo de temas, una de las cosas que a mí por lo menos me apasiona del mundo de la investigación...
I'm passionate about when it comes to operational research, data and models in general, is that you have this constant interaction with reality where systems are open. You don't model it and keep everything there. You need to have feedback from reality. And in that sense, here we have 2 people who will contribute a lot. We have Bernhard from GEC. There's a particularity to them. They worked in several countries of the region, and talking about these things, we found it interesting to talk about things more specific, practical from his experience. And one of the things that we find in common with Bernhard is that they develop a lot of work when it comes to collection of data automatically from the countries, which is something that's close to my heart because I do that too. And also, they deal with all of us just as we all do. So they have the same issues we all have. I think it would be interesting if they could tell us about the initiatives and what are the main challenges in the region.
Falta de estructura tecnológica en términos generales, falta de capacitación, falta de capacidades.
It could be lack of training, capacities, and those could be countries that are very linked with these problems. How are you planning today from G and Z, everything related to transmission lines where renewables are everywhere and we are running out of transmission? Thank you, Ivo. Good afternoon. In order to keep languages in Spanish means just trust in the data and statistic. You manipulate it yourself. And that's the thing, right? You started very well. Great data in the world and open source as well. I agree with you. It's important to have this data. And we have a lot of tools in the region, technical innovation. We have an MRV platform for public working. Something important is also efficiency in Brazil. We've been working with small companies looking for monitoring their energetic efficiency. And we are going to a subject close to my heart. We're always talking about installing more and more in generation, but for generation we need transmission. And what happens with energetic transmission? We could be more efficient and then continue with the plans of expansion, etc. Because GIZ, our project Pro Transition, we also have a forecast control. I understand there's one in Peru as well, and that helps a lot to support the generation and after the transmission, so as to see how the network's going to perform. You know, the eolic maps, solar maps, I don't need to talk about this, but it's something really simple that we need to talk about. There are so many digital advances nowadays, and for us it's really important to see or strengthen the capacities on one hand and the human development on the other. That's really important because the specialists in the companies don't have anyone who can manipulate those data and can interpret them. So we reached the first problem, and in many countries represented happens, is the standardization of processes. And we need models and translate them. And we need to respect these needs and the several models that we have from each country. I will mention some jams that we are attacking right now because transmission's not enough. We know that. I don't know if any of you have been to Germany recently. We have been talking about establishing a transmission line from the north to the south because we have a lot of wind in the north, but the whole Germany is in the south and we don't have enough transmission. So interconnection between countries is important as well, is something that we are looking at, and it would be interesting. And with the data that we are generating, it could be more efficient. Second thing, data, because the regulators sometimes don't talk with operators and operators with planners. If we don't solve that, we will not strengthen the capacities of everyone. And that's one of the basic steps we need to take. And as GIZ, with the platform that we have, we are supporting planners. Institutional capacities, mentioned that before. We need enough human resources, but where are the people with experiences? I see that Max, you, Galen, you two will be distributed among all of us because we don't have enough people. Well, we have 3, 4 people who does this, but you have a lot of work right now. The weak coordination between ministries and the regulators, that's also clear to reach an agreement as a country or regional level as a country. And you said it before, the quality of the data. Perfection is enemy of what's good. That data we can work and handle this electric system. And to wrap it up, if we did it, we need to have good data, the capacity, the coordination. We need a real tool to make energetic policies. And I want to close with a question. You have been for over 10, 15 years in the world of energy. And were we certain with the forecasts 10 years ago? Because I don't see anything that we forecasted 10 years ago. So maybe with that, we can do more and create more trust for planning. Thank you very much. Thank you, Bernhard. We will do the last change here and we'll give the floor to Felipe. He's a very interesting person because he's the managing director of Accenture, but he's a pioneer with the use of decarbonization in empresarial terms. We had talked a bit about looking forward, because the ones over here know what a mathematic programming program is. It's something related to algebra, a lot of problems. It's hard. And now we have great artificial intelligence, and it says, well, everything you learn is not useful anymore because I can solve that with a prompt. Of course, that's not true. I don't believe that, but it's what they sell. And the truth is, beyond the personal point of view that we might have, the future is wonderful or apocalyptic. The reality is that there are tools for machine learning, maybe not as much as artificial intelligence, that can be used for energetic planning. What can you tell us about that? Well, first of all, thank you for the invitation. It's a pleasure to be here to say hello to the people here in the panel. I'll try to speak Spanish. If it's not working, I'll go to English, and if not, I'll speak Portuguese. But I remember I had a econometry professor in the faculty who said that statistic was the science of torturing data until they say what you want to hear. It's a little bit like that. Well, I think we need to understand what's the origin of artificial intelligence. This started in the 50s, the machine learning models, but they haven't had success until recently, because for an artificial intelligence machine learning model to be effective, it needs data. And we just now have enough data. And since we all are addicted to data, we need to be aware of them. First of all, today, 50% of the data in internet are generated by artificial intelligence, synthetic data. So a lot of the information available, and I'm not talking about the energy sector, I'm talking about the internet. So you get an idea. In 2006, we created 18 zettabytes of information. In 2025, we are creating 180 zettabytes, which is 10 times more, with origin and synthetic data as well. So in this dynamic towards 2035, we'll get to 1 yottabyte, which is the biggest number in metrics until 2020 time. We created to solve this problem. But when you look at this universe of data that's so big and data that sometimes has multiple collinealities, it means that when you use one data for a provision, it replicates the same thing of another data. And when you use a lot of data with these characteristics, the model appears to be predictive, but it isn't, and that is a problem because we're speaking about the future. Another detail that's really important, and I think that's why artificial intelligence will solve all the problems, is that traditionally predictions that are projections are based in the past. So with zero verifiable characteristics of the past, they predict the future. Implicit in this technique is that the past, the facts are kind of steady. When we talk about climate change, it's not true anymore. I create projections based on the data that's verifiable, but it's not necessarily going to explain the future. So to answer objectively the question, I think the machine learning models are very good, mainly for short-term matters, because in the short terms, variables are kind of stable. So to improve efficiency of systems, load balance, that can be done. We have interesting cases about that. But when we look at long-term, that's harder because planning in based on projections that we know are hard because of the data and the change in the reality, I think that subjectivity and human reality are the most important that can affect statistics that are functional. So in order to wrap up on how it's complicated when you have too many data, there's a study that's very curious that concluded that the amount of sales of margarine has a correlation with the amount of divorces per the minute in the United States. If you look at the graph, they're completely compatible, but from that to conclude that one thing can predict the others, quite complicated, and that's evident. But when we are in a world of infinite data, not even correlations like this are obvious. So that's a problem for the data engineers. But yes, there's an important role, and we need to learn what's good quality data. And we need to create a model because this requires simplification, abstraction of reality without losing the capacity to answer questions. But I think I wanted to contribute. I know we had 2 questions for everyone, so thank you very much to the panel. It was great, everything you have taught us. Thank you.